Welcome to the deep dive. Today, we are looking straight up, but not just at the stars. We're really looking at the future, maybe the next evolution of civilization's core infrastructure.
Yeah, it's a big one. For the last, 2 decades, our computation, our energy grids, certainly our most advanced manufacturing, it's all been stuck here, bound by Earth's atmosphere, gravity, resources.
And those constraints are starting to pinch, right?
Right.
Especially with things like AI.
They really are. We're seeing this huge collision, you could say. It's driven by these exponential demands, technologically speaking. The sources we look at, they really hammer this home training and running these massive AI models, your GPTs, your Geminis, and whatever comes next.
The power consumption is just astronomical.
Astronomical is the right word. We're talking gigawatts of power.
Uh-huh.
And cooling water, millions upon millions of liters every year. Earth's a finite planet, we know that. But AI ambition seems pretty infinite right now.
So that pressure is forcing a pretty radical solution, moving things outwards. Extraterrestrial, really.
Exactly. So the mission today for this deep dive is kind of charting that great escape, if you will. We're looking at moving civilization's heaviest lifts, the most resource-hungry operations beyond gravity, beyond atmospheric hassles, beyond, frankly, a lot of terrestrial regulation, too.
The sheer scale of that kind of infrastructure shift,
Yeah,
it's almost hard to get your head around.
it is. So our deep dive today, it focuses on these three sort of interconnected frontiers. They really define what people are calling the new space economy. First up, space-based data centers, SBDC, designed to feed that AI hunger for energy and cooling.
Okay, SBDC.
Second, space-based solar power, or SBSP. The dream here is baseload clean energy, 247 beamed down.
Right, energy source.
And finally, orbital manufacturing, OM.
Oh, yeah.
This is about actually building things up there, materials, components, things that are maybe literally impossible to make under Earth's gravity.
Okay, let's unpack this because, we're fundamentally changing what the cloud even means. It's going from the sort of terrestrial metaphor to the actual cosmos. What jumps out at you first about the sheer engineering challenge here?
What really stands out, I think, is the intellectual elegance behind it. It's
Yeah.
not just, let's stick a data center somewhere weird. It's about fundamentally redesigning computation and industry to actually exploit the physics of space.
Exploiting the physics. How so?
It flips the script, Instead of fighting the environment, the heat, the gravity, the day-night cycle, you use it. The vacuum becomes your cooler. The constant sunlight becomes your power source. The lack of gravity becomes your perfect manufacturing condition. It's a total inversion. The universe stops being this barrier and actually becomes part of the infrastructure itself.
The universe as infrastructure. Okay,
yeah.
That's a powerful concept. Let's start there. So for decades, the cloud meant servers scattered across Earth. Now, the sources we read, they're not just talking hypotheticals. Major players are actively planning to put server farms hundreds of kilometers above us. A literal orbital cloud. Why? Given the incredible cost, why make this leap?
Yeah, the cost is huge, no doubt. But it really boils down to two, maybe three physical factors where space just offers these unbeatable advantages. Primarily, power and cooling.
Okay.
No matter how efficient we make our systems down here, we just can't escape the basic limits of the planet, right? The day-night cycle, the weather.
Right. On Earth, power, especially solar, is intermittent. You're fighting the clock, the clouds. But up there, particularly in certain orbits, that whole energy equation just flips on its head, doesn't it?
Completely flips. You go from intermittent to continuous power. That's the key. If you place satellites in what are called sun-synchronous orbits,
They stay in the sunlight all the time.
pretty much, they maintain continuous illumination, basically avoiding Earth's shadow. And the sources, they calculate that solar panels in space, they actually receive roughly 30% more energy per square meter compared to the best spots on Earth.
Just 30% more from being above the atmosphere?
Yeah, because the sun's energy isn't being weakened or attenuated by clouds, by haze, by the atmosphere itself. It's just raw, unfiltered sunlight.
Okay, 30% is a nice boost, but the continuous part, that sounds like the real economic game changer, especially for something like AI.
That's the core of it. It's the ultimate scaling solution for AI's energy needs. That continuous supply means these orbital data centers could, theoretically at least, hit something like 80–90% reductions in power costs.
80 to 90%. Compared to what?
Compared to a similar-sized facility on Earth that has to deal with building battery storage, grid connections, paying for power during downtime, all that stuff. When you're training a massive AI model that's gulping down gigawatts, turning that intermittent power source into basically an infinite 247 stream, That's the most direct path to solving the AI energy crisis.
Okay, so that tackles the power consumption side. That's huge, but it's only half the battle, right? The other massive energy sink is heat. We know data centers on Earth spend, what, almost half their energy budget just on cooling.
Easily.
Huh.
And consuming billions of gallons of water annually through evaporation towers, chiller systems. It's a massive environmental footprint just managing the heat.
And space, the vacuum, that offers a solution there too.
It offers the perfect passive antidote, really. The background temperature of deep space is hovering near absolute zero, Kelvin, that is.
Yeah.
So you have this unparalleled natural cooling efficiency.
Right.
Just there.
But hang on, I'm trying to picture this. Space is a vacuum. How does the cooling actually work? Down here, we use air flowing over chips, or
Wow.
liquid coolants touching the surface. Convection, conduction. You don't have that in space.
You've hit the key mechanism. You're right, no convection or conduction to speak of. In space, you rely almost entirely on thermal radiation. It's the only way heat can really escape in a vacuum.
So servers themselves radiate heat away.
Essentially, yes. You're basically turning the server racks or the whole facility into giant, super efficient radiators. Engineers design these enormous, specialized radiative cooling panels. Think of them like giant thermal mirrors attached to the server core. They just passively shed that waste heat out into the cold, empty void.
Because there's no air to trap the heat, and the vacuum acts like a perfect thermos bottle against heat leaking back in. It just radiates away constantly.
Exactly. And the beauty is, this mechanism is basically maintenance-free. Zero moving parts for the cooling itself. No pumps, no fans, no water. It saves all that electricity, and yeah, it saves those billions of gallons of water we use on Earth.
What's fascinating is the scale. You say using the universe itself as the heat sink.
It is. It's the biggest, coldest, most massive heat sink imaginable. You're just using the fundamental physics of space for temperature control. It's really quite elegant.
Okay, energy and cooling, those are compelling physics arguments. But you mentioned a third advantage earlier. What about the terrestrial constraints, like land security?
Absolutely. Those just
Yeah.
evaporate. Pardon the pun. The environmental and geopolitical upsides are potentially huge. Think about it. Zero terrestrial footprint. You don't need prime real estate. No battling for construction permits. No environmental impact studies for the site itself. You're not competing with farmland or ecosystems.
And resilience.
Unmatched resilience. Floating hundreds of kilometers up. You're above earthquakes, hurricanes, floods, tsunamis. All those natural disasters are irrelevant. And the sources also point out cyber attacks arguably become much harder. It's one thing to target a building with a physical address. It's another to target something moving at 17,000 miles per hour. You get physical isolation and strategic security baked in.
Okay, but let's push back on that zero footprint idea for a second. The operation might be clean, but getting all that heavy infrastructure up there, that requires rockets. Lots of them. Doesn't that create its own environmental headache? Trading ground pollution for atmospheric pollution.
That is the critical nuance, absolutely. And something we definitely need to keep front and center. The operational phase looks incredibly green. The deployment phase, not so much currently. That creates a major tension. It really underscores the need for cleaner, fully reusable launch systems, something we'll definitely circle back to in Part 4. But for now, the immediate economic drivers are all pushing towards grabbing these physics advantages: the power, the cooling, the location. Hashtag 1.2, the players and prototypes.
This really does sound like science fiction sometimes, but the sources we reviewed, they make it clear this is becoming industrial reality fast. And it's backed by some heavy hitters in tech. So who's actually out there building this luminous halo of computation around the Earth?
Well, the name that comes up early and often as a pioneer is Starcloud. It's a startup, but it has significant backing from NVIDIA. And their plan is, well, it's ambitious, a 5-gigawatt orbital data center constellation.
5 gigawatts, that's serious power. That's like several large terrestrial power plants dedicated just to this constellation.
It's massive. And NVIDIA's involvement tells you something important, right? This isn't just about storing cat videos. This is about high-performance computing, AI.
Right. NVIDIA makes the chips that power most large AI models.
Exactly. And their design philosophy for Starcloud apparently mirrors the tech it runs. The idea is that the modules themselves function almost like a physical neural network that autonomously optimize where the workloads run based on things like, which satellites have the best solar exposure right now, the latency needs for users on the ground, even managing radiation exposure over time.
An AI managing an AI data center in orbit, that's meta.
It is pretty meta, yeah. And of course, none of this really gets off the ground literally without the big logistical enabler.
Yeah.
SpaceX.
Ah, right. Musk.
SpaceX is just indispensable here. Elon Musk has been pretty blunt about it. His line is something like, Earth is for life, space is for computation. And he's building the tools. Starlink provides that necessary global, low-latency internet backhaul. And critically, Starship.
Hmm.
The reusable Starship platform is the only thing, really, that makes launching these multi-ton data center modules economically plausible at the kind of scale they're talking about.
It provides the sheer mass-to-orbit capability that older rockets just couldn't deliver affordably.
Precisely. You need to lift thousands of tons. Starship promises that. So it's this whole ecosystem play, isn't it? Starlink connects the orbital cloud, Starship builds it.
But it's not just one model, right? The sector seems to be specializing already. Some companies aren't focused on the heavy-duty, real-time computation.
That's right. Which brings us to another interesting player, Lone Star Data Holdings. Their niche is different. They're focused specifically on orbital data storage, pure archival.
Storage, like disaster recovery backups, or something more.
More like permanent archiving. Preserving humanity's most critical data, the non-replaceable stuff, cultural records, scientific data, maybe even DNA sequences, storing it in these orbital vaults designed to be super resistant physically and digitally. They've actually already contracted, I think the sources said 6 satellites with Sea to Space for this.
Wow, that's the Library of Alexandria 2.0 idea people talk about, putting our history above the chaos down here. That's got a huge cultural resonance.
It really does. And then on the more, perhaps, conventional business side, you have firms like Lumen Orbit. They're making this straight-up economic argument. Their calculations suggest space-based facilities could end up being 30–50% cheaper over a decade.
Cheaper, even with the launch costs.
Apparently, yeah. Once you factor in everything you avoid spending on Earth,
Yeah.
the energy, the cooling infrastructure, the land, the security, navigating terrestrial regulations, all those avoided costs add up. They talk about a self-expanding cloud where capacity just grows organically with each launch.
Okay, and then there's the most, I don't know, futuristic, the most radical idea linking computation and manufacturing, Besxar. They don't just want to run chips in space, they want to make them there.
Yeah, Besxar is aiming to actually manufacture semiconductors in orbit. And the physics rationale is pretty compelling. Microgravity allows for essentially defect-free crystal growth.
How does that work?
Well, down here, gravity pulls on the molten silicon or gallium arsenide, whatever they're using. That creates tiny imperfections, dislocations in the crystal structure. Those defects slow down electrons, generate heat, limit performance. In microgravity, you eliminate that pull. You can grow near-perfect crystalline structures.
Leading to
Better chips.
potentially vastly better chips, especially for AI processors, where purity and perfection translate directly into speed and efficiency. They think they can make AI accelerators in orbit that significantly outperform anything made on Earth.
That's pretty mind-bending. Making the tools for the orbital cloud in the orbital cloud, it's vertical integration on a cosmic scale.
Mm-hmm.
And then the ultimate validation perhaps came in, what was it, November 2025. Google's Project Suncatcher.
Ah, yes. When a hyperscaler like Google, with their capital, their engineering depth, their existing cloud infrastructure, when they jump in, it changes the game. It moves from niche startup territory to serious industrial reality.
Google is the accelerator, exactly. They announced launching prototype satellites in 2027. And these aren't just off-the-shelf parts. They're equipped with Google's own custom AI chips, the Trillium TPUs.
TPUs, tensor processing units. They're specialized machine learning chips.
Right. And crucially, they're radiation-hardened Trillium TPUs. That rad-hardened part is key. It means building in protection against that harsh space radiation environment, things like triple redundancy in circuits, special error-correcting codes. It adds huge complexity and cost, but it's essential for survival up there.
So Google's investing heavily in custom hardware, specifically designed for this hostile environment. And they're also tackling the data transfer problem. The sources mentioned terabit optical links.
Yeah, terabits per second using optical lasers, not radio waves. That gives you exponentially higher bandwidth to get the data back down to Earth, minimizing that communication bottleneck. So Google's basically validating the whole stack, the hardened compute, the high-speed links. Starcloud might have pushed the concept, but Google brings the scale, the integration power, the software expertise to really make Google Orbit, or whatever they call it, a potential reality.
Okay, that definitely sets the stage for the demand side. But running a 5-gigawatt orbital facility, let alone Google's ambitions? Well, it needs a 5-gigawatt power source. You can't really build the cosmic cloud without figuring out how to generate truly massive amounts of energy in space first.
You absolutely can't. Which brings us very neatly to our next frontier, space-based solar power.
All right, so now we're shifting focus. We're moving from the infrastructure that's consuming all this power, the data centers, to the infrastructure that could potentially generate it on an unprecedented scale. Space-based solar power, SBSP. The promise here is baseload, clean energy, beamed down to Earth 24/7. It sounds incredibly futuristic, almost like something out of science fiction.
What kind of is? The sources point out this is actually a really old idea, relatively speaking.
Yeah.
It was first imagined, seriously,
Yeah.
by the science fiction writer Isaac Asimov back in the 1940s.
Oh, Asimov, really?
Yeah. And then it was formalized scientifically by a NASA engineer named Peter Glaser in 1968. The thinking was, if the U.S. had really pursued it back in the 70s, it would have been an engineering challenge right up there with the Apollo program. It was seen as that big, that transformative.
Apollo program for energy. Wow. Okay, so how does this massive celestial relay system actually work? We're talking about generating power potentially 36,000 kilometers up in geostationary orbit and getting it down here reliably.
Yeah, the GEO orbit is often proposed because the satellite stays over the same spot on Earth. The system itself, it basically relies on three enormous principal components.
Okay, component work.
First, you have the orbital collectors. These aren't just small satellites. These are vast arrays of solar panels. We're talking potentially kilometers across, covered in ultra-efficient photovoltaic cells.
Kilometers. Okay,
Yeah.
that's huge.
Yeah.
Then what?
Second, you have the crucial bit, the energy transmission system. You can't just run a giant extension cord down from space, obviously. So the collected DC electricity from the panels gets converted into a high-frequency, tightly focused energy beam. Typically, this is microwaves, often around 2.45 gigahertz or 5.8 gigahertz.
Why those frequencies?
Because those frequencies travel through Earth's atmosphere, even through clouds and rain, with very minimal power loss, low atmospheric absorption. Sometimes lasers are proposed too, but microwaves are often the primary focus for large-scale power transmission.
Okay, so you've got giant collectors, a microwave beam. What catches it on the ground?
That's the third component, the ground-based rectenna. And rectenna is short for rectifying antenna. It's not a big dish like a radio telescope. Think more of a massive, open mesh-like network spread over a large area, maybe several kilometers across as well. It's made up of specialized dipole antennas with diodes that capture the incoming microwave energy and convert it back into usable AC electricity that can feed directly into the grid.
And how efficient is that conversion on the ground?
Remarkably efficient, actually. The sources claim these rectenna designs can achieve conversion efficiencies of up to 85%. That's converting the received microwave power back into grid electricity. It's very high for any kind of large-scale energy transformation.
Okay, the technology sounds plausible, if incredibly ambitious. But the real appeal, the game changer here, it seems to be solving the biggest headache of terrestrial renewables, especially solar and wind, intermittency.
Right. Solar only works during the day. Wind only when it blows. You need massive, expensive battery backup. SBSP eliminates that constraint almost entirely. That's the core value proposition. Because these orbital power stations are floating above the atmosphere, above the clouds, and crucially out of Earth's shadow for most, if not all, of the time, especially in GEO. They provide consistent, reliable baseload power. 24/7, 365.
And that allows countries to potentially do what? Retire coal plants.
Exactly. Retire carbon-intensive peaker plants, maybe even displace fossil fuel baseload generation entirely over the long term. It transforms solar from being just a supplementary source into a primary dependable grid supplier.
What's the actual performance difference? How much more power do you get from a panel in space versus on Earth?
Oh, it's stark. Terrestrial solar farms, on average globally, they have a capacity factor of maybe 20%. That means over a year, they only produce about 20% of their theoretical maximum output because of night, clouds, weather, season. In orbit, first, the panels receive much more intense sunlight, up to 13 times more energy flux than reaches the ground, according to some sources. And they can operate near 100% capacity, continuously. So the bottom line is orbital systems could deliver something like 5 to 10 times more actual energy per panel compared to the same panel on Earth over a year.
5 to 10 times more power delivered. That's huge.
It is. That consistency is everything for grid stability.
And the fact that you're beaming the power, that gives it incredible flexibility too, right? It's not tied to specific locations by wire.
Unmatched global reach. That's another massive selling point. SBSP could, in theory, beam electricity almost anywhere on the visible side of the Earth from its orbit. Think disaster zones where the local grid is completely knocked out.
You could set up a mobile rectenna quickly.
Exactly. Or remote villages, islands, military bases. Places that are currently incredibly expensive or difficult to connect via traditional cables. Or just supplement power to major cities during peak demand. You can redirect the power relatively easily just by repointing the beam from the orbital transmitter. It's a powerful tool, geopolitically and for humanitarian aid.
And if they can get the costs down, the projections seem pretty competitive.
Yeah, the long-term target cost, once the technology is mature and scaled up, is projected to be somewhere in the range of 3 to 6 cents per kilowatt hour.
Which is what? Comparable to ground-based solar today?
It's right in the ballpark, or potentially even cheaper than some conventional renewables or fossil fuels in many places today. And if you look at the really big picture, the World Economic Forum has suggested SBSP could potentially supply up to 10% of global electricity demand by 2050.
10% of global electricity. That's not niche. That's a massive slice of the pie.
It's huge. Yeah, that's roughly equivalent to all the hydroelectric power generated globally today. So we're not talking about a marginal solution here. If it works, it represents a monumental shift in how the world gets its energy.
Yeah.
Hashtag 2.2, the new energy space race.
Okay. Hitting that 10% target by 2050.
Yeah.
That requires building infrastructure on a scale that's just staggering.
Yeah.
Kilometers-wide structures in geostationary orbit. This has to be a global effort, right? It sounds like a new kind of space race, but focused on energy security.
It absolutely is. Energy sovereignty in the 21st century might well depend on having access to orbital power. So yeah, every major global space power is heavily invested, or at least exploring it very seriously.
What's the U.S. approach looking like?
The U.S., through NASA and the Department of Energy, seems focused on these complex, modular, self-assembling designs. NASA's big concept is called SPSL-SHAE. That stands for Solar Power Satellite via Arbitrarily Large Phased Array.
Catchy name.
Yeah. The core idea is using thousands of small, identical, maybe hexagonal modules that can assemble themselves or be assembled robotically in orbit. Modularity is key because you obviously can't launch a multi-kilometer structure in one go. It has to be built up there. And they're putting significant funding into microwave beaming experiments, too, validating the atmospheric transmission tech, ensuring it's safe, refining the beam control.
Meanwhile, across the Atlantic, Europe seems to be linking SBSP directly to their climate goals.
Very much so. The European Space Agency, ESA, has its Solaris program. They're looking hard at the technical feasibility, the economics, but also public acceptance, which is crucial. And major aerospace players like Airbus are actively testing modular SBSP designs. They explicitly see it as a potential contributor to Europe's net zero 2050 roadmap, providing that guaranteed clean baseload power needed to stabilize grids that rely heavily on intermittent terrestrial renewables.
In China, the sources suggested they have perhaps the most aggressive timeline.
They really do. China's National Space Administration, the CNSA, is apparently aiming for a megawatt-scale demonstrator in orbit by 2030.
2030, that's incredibly soon for something this complex.
It is very ambitious, and their longer-term goal is a full gigawatt-scale operational orbital power station by 2050. And this isn't just paper studies. They're already conducting quite advanced ground-based microwave transmission tests over significant distances in places like Chongqing province to really prove out the system's reliability and efficiency before they take it to orbit.
And it's not just governments, right? We're seeing private companies jumping in, too.
Absolutely. Private capital and innovation are crucial here. You've got companies like Varda in the U.S., and in the U.K., there's Space Solar, which has its Cassiopeia system. Both of those are reportedly planning prototype launches around 2027.
Cassiopeia, that one sounded interesting in the notes. Designed for Starship.
Yeah, Cassiopeia concept is apparently being engineered from the ground up, specifically to be launched in segments optimized for the payload capacity and fairing size of SpaceX's Starship.
Yeah.
They're betting heavily on Starship becoming the workhorse.
Which brings us back again to the great enabler, Starship. It's interesting because the sources cite Elon Musk himself being somewhat skeptical about SBSP's economics, calling it economically marginal at one point.
Yeah.
Yet his rockets are the key.
It's a fascinating paradox, isn't it? The sheer logistics are the historical choke point for SBSP. Building and launching these massive arrays, kilometers wide, into GEO 36,000 kilometers up. The cost with traditional rockets was simply astronomical, running into the trillions, making it totally non-viable economically.
But Starship changes that calculation.
Fundamentally, if Starship achieves its goals of full, rapid reusability, it promises to slash launch costs dramatically, down from thousands of dollars per kilogram today, potentially to the $100 per kilogram range, maybe even as low as $10 per kilogram eventually. That radical cost reduction is the single biggest factor that could actually make SBSP commercially viable. Without it, it likely remains a technical curiosity. With it, the whole picture changes.
So the takeaway here is SBSP is technically within reach, the physics works, but the economics are tough. and entirely dependent on achieving those ultra-low launch costs. Commercial viability is probably still a couple of decades out, 2040s, 2050s.
That seems to be the consensus timeline. Yeah, 2040, 2050 for large-scale commercial deployment. It's the ultimate long-term investment, maybe the ultimate moonshot for global energy independence. It demands decades of sustained R&D, massive capital investment, and crucially, that revolution in launch capability.
Okay, so if space-based data centers are about putting the brain in orbit and space-based solar power is about powering it, then orbital manufacturing OM is about, well, about building the really advanced stuff up there too. The vision here seems huge, shifting heavy, maybe polluting industry off Earth, allowing the planet to recover. The sources mentioned restoring Earth as a global garden. That's ambitious.
It's a very grand, long-term vision, certainly inspired by thinkers like Gerard O'Neill back in the 70s. But the near-term focus of orbital manufacturing is more specific. It generally covers about three overlapping domains right now.
Okay, what are they?
First, there's in-space servicing, assembly, and manufacturing, often shortened to ISAM. Servicing is things like repairing or refueling existing satellites, essential for sustainability. Assembly is constructing those really big structures we talked about, things too large to launch folded up, like giant space telescopes, maybe components of those SBSP arrays, or even sections of future space stations or habitats. They get launched as parts and assembled robotically in orbit.
And the third part, the M in ISEM, true manufacturing.
Right. True fabrication. Taking raw materials or precursor materials launched from Earth and processing them in space into finished high-value products. And this is where the unique physics of space really comes into play again.
It all comes back to the physics advantage, doesn't it? This time, it's microgravity.
Exactly. It's predicated almost entirely on the microgravity advantage. Down here on Earth, gravity is constantly interfering with processes at a microscopic level. It causes fluids to separate or convect unevenly. It makes materials sediment. It induces stress and defects in crystal structures as they solidify.
But in orbit, with gravity effectively neutralized, those problems disappear.
They largely do. Fluids behave differently. Surface tension becomes dominant. Materials mix more uniformly. Crystals can grow without the stress and imperfections caused by their own weight. This allows for possibilities that are just incredibly difficult or sometimes impossible to achieve terrestrially.
Okay, so what's the killer app? What's the most valuable product that gets a huge boost from being made in microgravity?
Well, the sources highlight a few key areas where the material science is potentially transformative. We already mentioned defect-free semiconductor production with Besxar, growing perfect crystals for faster chips. But maybe the clearest, most commercially advanced example right now is a special type of optical fiber called Zeblan.
Zeblan? What is it?
It's a type of heavy metal fluoride glass. It has the theoretical potential to transmit light and therefore data with much lower loss than the standard silica fibers we use for internet cables today.
Okay, so why make it in space? What's gravity doing to fiber optics on Earth?
When you draw any optical fiber on Earth, pulling it from molten material, gravity inevitably causes microscopic imperfections, tiny crystals forming within the glass structure, density variations. These effects scatter the light signal as it travels through the fiber. That scattering limits the distance the signal can travel and the bandwidth, the speed of data transmission.
And in microgravity?
Those gravity-induced crystallization defects are drastically reduced or eliminated. The Zeblan fiber comes out much closer to its theoretical perfection. And the result, according to the sources we looked at, is a fiber that could potentially enable data transmission maybe 100 times faster than the best silica fibers currently deployed.
100 times faster, just from getting gravity out of the manufacturing process? That's incredible. That's a direct, tangible benefit from changing the physics of the factory floor.
It really highlights the potential, yeah. And another huge area is pharmaceuticals, the pharma benefit.
How does microgravity help make drugs?
It's about protein crystallization, mainly. Growing highly ordered, pure crystals of complex drug molecules is crucial for understanding their structure and function and for formulating effective medicines. But large, complex molecules often resist forming good crystals under gravity.
They clump together wrong or form tiny, flawed crystals.
Exactly. Microgravity allows these molecules to assemble more slowly, more perfectly, with far greater structural precision. This enables the growth of larger, ultra-pure crystals of complex drugs, like some antivirals mentioned, ritonavir, remdesivir, were examples given.
And why does a better crystal matter for the patient?
A more perfect crystal structure can significantly improve the drug's properties. Better solubility, meaning it dissolves more effectively in the body. Better bioavailability, meaning more of the active drug gets absorbed. Ultimately, potentially higher efficacy, and maybe even fewer side effects.
And this isn't just about slightly better drugs, is it? There's a big R&D cost implication too.
Absolutely. The research suggests that being able to grow these high-purity crystals reliably in microgravity could streamline the whole drug development process. You understand the molecule better, faster, you can optimize formulations more easily. Some estimates suggest it could cut drug R&D costs by maybe up to 40% in certain cases. Space becomes this unique, high-value industrial park for biotech and advanced materials, R&D, and eventually production.
Are there other advantages to manufacturing in orbit beyond just microgravity?
Yeah, a couple of the same ones we saw with data centers apply here too. First, that constant, intense solar illumination gives you 247 power for running your factory processes. Second, and this is maybe more subtle but really important for things like semiconductors or sensitive optics, the natural hard vacuum of space.
It's like a perfect clean room.
It's the ultimate clean room, and it's free. Down here, building and maintaining the ultra-clean environments needed for something like chip fabrication costs billions. You're constantly fighting dust particles, contaminants, in space. The vacuum itself is an intrinsically contamination-free environment, far purer than anything achievable on Earth.
Okay, so that philosophical vision moving heavy industry off Earth starts to seem less like a dream and more like, well, like an economic strategy for certain high-value products. Does the market potential reflect that?
The projections are definitely bullish. Analysts are estimating that orbital manufacturing, just focusing on these initial high-value areas like Z-band fibers, specialized semiconductors, and pharmaceuticals, could rapidly grow into a $10 billion to $20 billion per year industry by 2030.
10 to 20 billion by 2030, that's not insignificant.
Not at all. And looking further out, towards 2040 and beyond, if you include the potential for in-space resource utilization, asteroid mining, large-scale construction, the total value of orbital infrastructure and industry could run into the trillions. This really feels like the moment where those foundational ideas from Gerard O'Neill about space settlements being enabled by using space resources and building things in space start colliding with 21st century realities like AI, robotics, and advanced material science. It's becoming tangible. Hashtag 3.2, Builders in the Abyss.
So who are the companies actually doing this now? Who are the pioneers firing up these orbital forges today?
Well, in that critical area of orbital pharmaceuticals, the clear vanguard, the company that's really proven the concept, is Varda Space Industries.
Varda, right. They had that successful return mission recently.
They did. It was a monumental milestone. They successfully manufactured drug crystals in orbit, specifically ritonavir crystals, inside their autonomous capsule, and then crucially, they managed the safe, controlled atmospheric re-entry and recovery of that capsule with the high-value product intact.
Proving the round trip is just as vital as proving the manufacturing, isn't it? If you can't get the stuff back reliably and affordably, the whole thing's pointless.
Exactly. Varda proved the entire chain. Orbital production, quality control in space, and successful return. That's huge validation.
And then we circle back to Besxar again. They're not just making chips, they're a manufacturing play too.
Right. Their whole focus is orbital semiconductor fabrication, using that microgravity advantage to make those potentially flawless AI accelerator chips, free from Earth's gravity-induced thermal distortions during manufacturing. They seem deeply invested in planning launches, using specialized fab ship concepts, likely banking heavily on Starship's future capabilities.
And the companies building the actual space stations, the destinations in orbit, they must see manufacturing as part of their business model too.
Ooh, absolutely. Look at Axiom Space. They're building Axiom Station, which is intended to be the first major commercial orbital platform, eventually replacing or supplementing the ISS. And their design, from the very beginning, integrates dedicated, flexible manufacturing bays.
So companies could rent space on Axiom Station to do their orbital manufacturing.
That's the idea for biotech, for material science research, potentially for small-scale production. Axiom aims to be this global hub, this orbital industrial park, accessible to researchers and companies from various countries and industries.
And scaling any of this up, building the SBSP arrays, assembling data centers, running factories, it all seems heavily reliant on robotics and automation, right? You can't just send astronauts up with wrenches for every task.
No way. Robotic automation is absolutely critical for the scalability and economics of all three of these frontiers, SBDC, SBSP, and OM. We're seeing companies specialize here too. Rocket Lab, for instance, they're working on developing autonomous on-orbit assembly drones or robots specifically designed for building large structures like mega constellations.
And even more specialized manufacturing tech.
Yeah, there are companies like Orbital Composites. They're pioneering things like large-scale carbon fiber 3D printing in space. Imagine autonomous robots extruding and curing huge composite structures. Satellite frames, booms, maybe even massive components like lunar gyroscopes for stabilization entirely assembled or even manufactured from raw stock in orbit.
Okay, here's where it gets really interesting for me. This shift. It fundamentally changes what made in could mean. We're moving beyond just launching fully finished satellites or components. We could be launching relatively cheap, basic feedstock spools of carbon fiber, tanks of precursor chemicals, silicon wafers, and then letting autonomous robots use the unique physics of space, the microgravity, the vacuum, the constant solar power to fabricate the truly high-value, complex goods in situ.
It's the ultimate expression of lean, maybe even off-world manufacturing, isn't it? Potentially zero pollution generated on Earth for that specific process, perfect material purity, effectively unlimited physical space to build, 247 solar power, and all overseen by autonomous AI systems. It's a paradigm shift.
It is. But that final piece you mentioned, autonomy, robotics, operating in the most hostile environment imaginable with no easy repair options, that takes us squarely into the massive shared challenges facing all three of these ambitious space frontiers. Okay, it's easy to get swept up in the sheer coolness of this, right? Unlimited clean power, perfect computer chips made in space. But the sources we compiled, they were also very clear about the flip side, the immense technical hurdles, the staggering costs, the ethical quandaries. Space is beautiful, but it's also, as you said, brutally unforgiving, especially to complex hardware.
Absolutely. The challenges are monumental. They really cut across SBDC, SBSP, and OM equally. Hashtag 4.1, technical and reliability nightmares. The first, most pervasive threat is radiation. As soon as you leave the protective bubble of Earth's magnetic field and atmosphere, everything is constantly bombarded. High-energy protons from the sun, solar flares spitting out particles, galactic cosmic rays coming from deep space. It's a shooting gallery at the atomic level.
And this damages electronics?
Severely. The sources mention the International Space Station, which is still partially protected in low Earth orbit, experiences hundreds of radiation-induced single-event upsets every year. That's where a single high-energy particle strikes a memory chip or processor and flips a bit, changes a 0 to a 1 or vice versa. That can corrupt data, crash software.
And you can't just reboot easily. How does this impact the hardware cost? Fixing this isn't simple, I assume.
It's incredibly expensive. The cost of making electronics durable enough, radiation-hardened or rad-hard, is astronomical. A standard microprocessor you might buy for, say, $300 on Earth. To make a functionally equivalent chip that can reliably withstand the space radiation environment, that might cost $200,000 or more.
$200,000 for one chip. Why so much?
It involves entirely different manufacturing processes, things like using silicon on sapphire wafers instead of pure silicon. It requires building in multiple layers of redundancy at the circuit level, like triple modular redundancy, where you have 3 identical circuits doing the same calculation, and a voting system picks the majority answer if one gets zapped by radiation. Plus, complex error-correcting codes built into the hardware and software. All that drives the cost through the roof. And that cost applies to every single component in an SBDC, an SBSP control system, or an OM robot.
Right, so radiation is a killer. Then there's the thermal problem. We talked about the vacuum being a great heat sink for radiative cooling, but you mentioned it also creates the opposite problem, thermal shock.
Exactly. It's a paradox of the vacuum. Space is empty, which is great for radiating heat away eventually.
Yeah.
But that passive radiation is actually incredibly slow compared to, say, dunking a hot chip in liquid coolant on Earth. And compounding that, orbital facilities experience these violent temperature swings.
Right, sunlight versus shadow.
Yeah, you can go from maybe plus 120 degrees Celsius, that's boiling hot, when in direct, unfiltered sunlight, down to maybe negative 100 degrees Celsius, incredibly cold, just minutes later when the satellite passes into Earth's shadow. That happens every orbit in LEO, maybe less frequently, but still significantly in higher orbits.
Those huge rapid temperature swings, that must just wreak havoc on materials, on electronics.
It induces massive mechanical stress. Things expand in the heat, contract violently in the cold, solder joints crack, materials fatigue, components warp. It's one of the toughest, most persistent engineering challenges. Managing that thermal cycling requires very sophisticated active thermal control systems, heat pipes, pump fluid loops, deployable radiators, and if those systems fail. The passive cooling alone might not be enough to stop components from frying in the sun or freezing in the shade. Catastrophic failure is a constant risk.
Okay, radiation, thermal extremes. What about just talking to these things? Communication. A cloud isn't much use if you can't access the data, a power station isn't useful if you can't control it, and space is big.
Communication is a huge hurdle. It comes down to basic physics again, the inverse square law. Signal strength drops off dramatically with distance. For something like a 5 gigawatt SBDC to be useful, you need incredibly high bandwidth links back to Earth terabits per second, as we mentioned.
Which requires lasers.
Primarily, yes.
Yeah.
Massive, precisely aimed optical laser links. But even with lasers, achieving that kind of bandwidth reliably, consistently, through the atmosphere, it's incredibly difficult. Weather can interfere, you need complex pointing and tracking systems. It's a major bottleneck.
And even if you solve the bandwidth problem, you can't beat the speed of light itself, right? Latency, the delay.
Correct. That's an immovable constraint to physics. Even from low Earth orbit, just a few hundred kilometers up, the round-trip time for a signal to go up and come back down is inevitably going to be somewhere in the range of 20 to 50 milliseconds. Minimum.
And 50 milliseconds. That sounds fast, but is it fast enough?
It's perfectly fine for many things, streaming video, web browsing, email. But for applications that need truly instantaneous response, it's fatal. Think high-frequency financial trading, where they measure delays in microseconds. Or think about real-time AI inference, maybe controlling autonomous cars or critical robotics on the ground from an orbital AI. That 50 millisecond lag, it's just too slow. It could be dangerous.
So the cosmic cloud might be perfect for huge non-real-time tasks like training the next monster AI model or massive scientific simulations, but it won't replace everything the terrestrial cloud does, especially not the low-latency edge computing stuff.
Not without some radical breakthrough in physics that lets us communicate faster than light, no. And then there's maybe the most daunting challenge of all, maintenance and reliability.
Yeah.
Up there's no IP support desk you can call.
Right. If a server rack fails or a solar panel gets hit by a micrometeoroid, what do you do?
Yes, exactly. Repairs require multi-billion-dollar robotic servicing missions, maybe eventually astronauts, but that's incredibly complex and expensive. Hardware upgrades. Forget swapping out a component. It basically means launching an entirely new replacement module or satellite. So these orbital facilities, the data centers, the power stations, the factories, they have to be designed for incredible longevity and autonomy from the start.
They need to be self-healing.
Essentially, yes.
Yep.
They need to be autonomous, capable of operating without human intervention for years, maybe decades. They need to detect faults, isolate problems, reroute functions, maybe even perform robotic self-repairs. It requires this perfect triad, really. Sophisticated machine learning for autonomous operation, incredibly fault-tolerant hardware designed for durability, and advanced robotic systems for maintenance and repair. It's an enormous systems engineering challenge. Hashtag TAG 4.2. Economic and environmental paradoxes.
Okay, let's pivot slightly to the money. This all sounds fittingly astronomically expensive. How do the economics actually work? How do we square these multi-billion, maybe trillion-dollar initial investments with the long-term promise of cheap energy or computation?
The astronomical cost is, without doubt, the single biggest barrier right now. It shapes everything. Current launch costs, even with reusable rockets like Falcon 9, are still hovering around $1,500 per kilogram to low Earth orbit. Higher orbits like GEO are much more expensive.
So just launching, say, a single server rack, how much would that cost?
Well, a big, dense server rack might weigh, let's say, 500 kilograms. At 1,500 kilograms, that's $750,000 just for the launch. And that's before you factor in the cost of the hardware itself, which, remember, might include those $200,000 rad-hardened chips. Building a full-scale SCC or kilometer-wide SBSP array, you're talking billions, potentially hundreds of billions, or even trillions for the full vision.
Which just reinforces the point about Starship, doesn't it? The entire economic viability of this whole new space economy seems to hinge on Starship achieving its really aggressive cost targets.
It absolutely does. For these concepts to move beyond prototypes and government-funded missions into truly large-scale, commercially viable infrastructure, launch costs have to plummet. We need to get well below, say, $200 per kilogram by the 2030s.
Right.
And ideally down into that $10 to $100 per kilogram range that Starship is promising eventually. Until that happens, these remain incredibly capital-intensive projects, reliant on huge venture investments or sustained government backing. They just can't scale globally otherwise.
And the high cost of lifting stuff up is only one side of the economic coin, isn't it? There's also the growing cost or risk associated with the stuff that gets left behind up there, the debris dilemma.
Ah, yes. The Kessler syndrome. This is maybe the most existential threat hanging over all three of these space frontiers. It's named after the NASA scientist Donald Kessler, who predicted it back in the 70s.
The idea that collisions create more debris, leading to more collisions. A runaway chain reaction.
Precisely. Earth's orbit, especially LEO, is already worryingly crowded. The sources cite over 36,000 tracked debris objects larger than 10 centimeters. Things like dead satellites, old rocket stages, fragments from past collisions, or ASAT tests. And those are just ones big enough to track. There are millions of smaller, untrackable pieces, and they're all whizzing around at incredible speeds up to 28,000 kilometers per hour, or 17,500 miles per hour. A tiny paint fleck at that speed can hit like a bullet.
So if we start launching thousands of new SBDC nodes, these vast kilometers-wide SBSP arrays, multiple orbital manufacturing platforms, the risk of a collision just skyrockets.
The risk multiplication is potentially exponential. A single significant collision between two large objects or an impact on a large structure could instantly create a cloud of thousands of new lethal debris fragments. Each of those fragments then increases the probability of further collisions. It could trigger a cascading effect that renders entire orbital altitudes, maybe the most valuable ones like sun-synchronous LEO, completely unusable for generations, for centuries even.
That would kill the entire space economy before it even gets started.
It absolutely could. The sources really stress this. Orbital expansion, on the scale we're talking about, without mandatory, globally enforced protocols for satellite design, for deorbiting, for active debris removal technologies, for responsible space traffic management. It's effectively courting disaster. It's a classic tragedy of the commons problem, playing out hundreds of kilometers up with no clear international sheriff to enforce the rules.
And then there's the environmental paradox we touched on earlier. We're moving industry to space partly for green reasons, to protect Earth's environment, but the rocket emissions themselves have an impact, don't they?
They do, and it's a painful trade-off, especially with current and near-term technology. Every rocket launch, particularly those using traditional solid rocket boosters or hypergolic fuels, injects significant amounts of pollutants directly into the sensitive upper layers of the atmosphere. We're talking soot particles, alumina particles from solid rockets, water vapor, nitrogen oxides.
And what do those do up there?
They can persist for a long time at those altitudes. Soot and alumina particles can damage the ozone layer. Water vapor, injected high up, can act as a potent greenhouse gas and form high-altitude clouds that affect Earth's energy balance. The sheer volume of launches required for industrial-scale orbital infrastructure. The cumulative atmospheric impact could potentially negate some, or even all, of the long-term green benefits of moving industry off-planet.
So these projects can't really claim to be truly sustainable until the launch systems themselves become much cleaner. Things like methane-fueled reusable rockets like Starship aims to be, or maybe future hydrogen-fueled systems.
That seems to be the case. We need launch technology that minimizes both the cost per kilogram and the atmospheric pollution per launch. Until then, we're essentially trading short-term, potentially significant atmospheric pollution for the promise of long-term planetary sustainability benefits. Closing that gap, cleaning up the access to space is absolutely crucial for the ethical case for this whole endeavor. Hashtag 4.3. Political and ethical void.
Okay, last major area of challenges. The political and ethical dimensions. Space law, geopolitics, the fundamental questions about who owns space, who benefits. The foundational treaty, the UN Outer Space Treaty of 1967, was written in a very different era, wasn't it? When space was mostly about peaceful exploration by superpowers.
It absolutely was. It declared space the province of all mankind, prohibited national appropriation, banned weapons of mass destruction in orbit. Noble principles. But it's critically showing its age now that space is rapidly becoming a zone of intense commercial activity, resource competition, and potentially military confrontation.
How does that old treaty handle something like, say, a giant orbital data center run by a multinational corporation?
That's where it gets incredibly fuzzy. The legal questions are complex and largely unanswered. If these data centers, holding sensitive data from potentially millions of people or multiple nations, are orbiting Earth, crossing national borders dozens of times a day, which countries' laws govern the data they hold? Does data sovereignty follow the satellite or the user on the ground? Who is liable if there's a data breach or if the satellite causes damage? Does the nation that launched the satellite maintain jurisdiction over the computation happening inside it, even if the customer is elsewhere?
We need a whole new legal framework, don't we? A digital celestial regime.
Something like that seems urgently needed, yes. A framework to govern data rights, liability, resource extraction rights for future asteroid mining, orbital traffic rules, debris mitigation responsibility, all the complex issues arising from this new industrial era in space. Without it, we risk a chaotic, conflict-prone, Wild West scenario.
And these incredibly valuable orbital assets, power stations, supplying cities, data centers, running economies, they inevitably become strategic military targets, don't they? Warfare and vulnerability must be a huge concern.
It's a massive concern. These orbital assets offer physical isolation in some ways, but they also create profound political and military vulnerabilities. We know that anti-satellite ASAT missile technology exists. Major powers like the US, Russia, China, India have demonstrated the capability to destroy satellites in orbit, often creating huge debris clouds in the process.
So a fixed multi-billion-dollar piece of infrastructure like an SBSP array or a large SBDC, it's basically a sitting duck.
It's extremely vulnerable, yes, not just to kinetic ASAT missiles, but potentially to less destructive but equally disruptive threats, high-powered lasers that could blind sensors or damage solar panels, high-power microwave weapons that could fry electronics, cyber attacks targeting the control systems. When nations become reliant on orbital infrastructure for critical functions like energy or computation, protecting those assets becomes a primary national security imperative. This inevitably creates geopolitical tension and fuels the risk of space weaponization. Space offers isolation, but it absolutely multiplies political and military exposure.
Which brings us, I suppose, to the biggest, broadest question hanging over all of this, the moral weight, the ethics of this grand expansion. Are we genuinely solving Earth's problems of scarcity and pollution by moving industry upwards? Or are we just exporting our potentially exploitative habits, our conflicts, our waste problems into a new domain?
That is the fundamental ethical dilemma highlighted in the sources, isn't it? The cosmic cloud, the orbital factories, the power beams, they promise this incredible mastery over nature, over energy, over information. But we have to be incredibly careful that this expansion doesn't just become another chapter in the history of human exploitation, another pristine environment turned into an industrial zone, another arena for geopolitical conflict.
So the challenge isn't just technical or economic. It's about ensuring this whole venture is guided by principles of sustainability, peaceful use, equitable benefit, making sure orbit becomes a genuine sanctuary for knowledge and progress, not just a mirror of Earth's past mistakes and excesses.
Precisely. That's the hope and also the profound responsibility that comes with this technological leap. Hashtag cat outro.
So where does this leave us? We've journeyed through three absolutely massive, potentially trillion-dollar ideas today. Moving AI computation to orbit with SBDCs, generating clean baseload power from space with SBSP, and creating impossible materials through orbital manufacturing. They're all converging, all feeding into each other, all happening in the orbital sphere above us. It's a stunning marvel of human imagination and engineering ambition.
It really is. But as one engineer was quoted, rather wryly in the sources, the easy part isn't getting, say, a radiation-hardened GPU into orbit. We know how to launch things. The hard part is conquering the zillion problems afterward. The radiation, the thermal extremes, the latency, the debris, the cost, the maintenance, the politics.
That technological holy trinity you mentioned earlier.
Yeah. Succeeding on this scale seems to require this convergence. Incredibly sophisticated machine learning for autonomy, fundamentally fault-tolerant hardware designed for decades of survival, and advanced robotic systems for assembly and self-repair. The sources seem to agree. The fourth industrial revolution, driven by AI, might literally be powered and perhaps even built using starlight and the vacuum of space.
The scale of the ambition, that's what really sticks with me. We're not just talking about building new gadgets or services. We're talking about architecting and constructing an entirely new multi-trillion-dollar nervous system, maybe even industrial base for human civilization, and one that's physically detached from the planet itself.
Which leads us right into that final provocative thought, maybe for you, the listener, to mull over. The sources kind of nudge us here. They remind us that throughout history, humans have built monumental infrastructure, often to express these deeper, almost metaphysical ambitions, right? The pyramids reaching for eternity, the cathedrals soaring towards faith. Even modern terrestrial data centers, in a way, are monuments to this new god of intelligence.
That's an interesting parallel.
So the question becomes, if we are truly moving our computation, our thinking machines, and our most advanced industry to the stars, if we are physically creating this second brain for humanity in orbit, what kind of spiritual or philosophical weight will that entity carry for us down here? What does it mean for our identity as a species anchored to this planet?
And what price Ethically, environmentally, geopolitically, are we really willing to pay to achieve that ascent? Knowing all the immense risks and challenges we just discussed, the debris, the potential for conflict, the atmospheric cost of getting there.
Exactly. It's not just about the technology, it's about the wisdom to wield it responsibly. And that's knowledge, that perspective, that should hopefully influence how you view every single rocket launch you see streaking across the sky from now on. It's not just cargo, it's the building blocks of a potentially very different future.